Welcome everyone to Sharcnet General Interest Seminar. The topic today is Introduction to MPI Part 3. I am Paweł Pomorski. I am based at University of Waterloo and working for Sharcnet, and this is my email address. Now, this presentation is a bit unusual for us in that it is part of a series. So we had Part 1 and Part 2 already. And this presentation assumes that you have seen the two previous parts, and we are just picking up where we left off. So if you have not seen them, then please visit our YouTube channel. You can find it by searching for Sharcnet and find the two previous parts. So in Part 1, we introduced MPI itself with the basic essential operations like MPI Send and Receive. So this was Part 1. And then in Part 2, that was the seminar given by myself, I was covering more advanced features like collective communications, broadcast, reduce, etc., and non-blocking communications, which allow you to overlap communication with computation. So this was Part 2. And now we are moving on to Part 3. So in this part, I want to cover two additional advanced MPI concepts. One of them is, the first one is user-defined data types, and the second one is user-defined communicators and topologies. So why do we need a user-defined data type? We need it because communication always has overheads. So whenever you're sending a message, no matter how small this message is, there's always a fixed non-zero cost to send any message. So if you are sending multiple small messages, then to avoid this cost, it is much better to combine the content of these multiple smaller messages into one larger one, and then you're just sending one message. So that means that this basic essential cost of sending a message, you're incurring it only once instead of multiple times. Now, we can already do simplest grouping with MPI Send and MPI Receive, which we have seen in previous lectures. So if you, let's say, want to send 10 floating point numbers in an array, you don't call MPI Send 10 times. Instead, you provide the initial address of the array, starting address in this variable, and then you provide the count. So this is how many items you want to send. You provide the data type of the item you're sending. And this allows you to send multiple items in a single message. And this will work fine as long as your data is contiguous, so it's sitting in a single array, and as long as your data consists of identical types, and these types have to be conventional. They have to be integer or float, and so on. But nevertheless, even the basic MPI Send and MPI Receive already allow you to group data together. But what happens if you want to send a more complicated data structure? So let's look at an example of one here. Now, this isn't a very complicated data structure. Actually, it consists only of a floating point number, floating point number, floating point A, floating point B, and an integer n. And we group this in a single data structure. We call it ndata_t. So what would happen if we try to send this data using an MPI command, where we, instead of a data type, we indicate what is the structure type that you want to send? Well, this will not work because we have a function here, and arguments to functions in this case must be variables, and they cannot be defined types. So we need a way to define a type that can be used as a function argument. In other words, a type which can be stored in a variable. And MPI provides precisely such a type. It's called MPI_data type. So let's continue with this particular example. Let's say that I have a program, and I have variable A, variable B, and variable n. And let's say that the first variable is stored at address, let's say 24. Second variable B is stored at address 40, and last variable is stored at address 48. And the contents are, well, the content of this address is 0.0, the content of this one is 1.0, and the content of this one is 1024. And if we want to picture this in a graphical way, here's what this would look like. So here's a memory, and memory, you can think of the memory just a giant one-dimensional vector. So here is my variable A at position 24. Here's variable B at position 40. Here's variable n at position 48. And these are the relative displacements between the start of A and the start of B, and then the start of A and the start of n. So if I want to send this data structure in one go, I need to provide the following information. I need to indicate that there's 3 elements to be transmitted. Their types have to be indicated. In this case, it will be float, and integer. And the relative displacement from the beginning of the message has to be indicated. In this case, 0, 16, and 24. And finally, when I'm sending, I have to provide the address of the beginning of the message, which will just be the address of A. So we will have to then create a new data type, which will store the information from 1, 2, and 3. And then each of the receiving processes can determine exactly where the data should be received. So the principle behind MPI's derived types is to provide all the information except the address of the beginning of the message of the new MPI data type. So then when you call MPI Send or MPI Receive, you just provide the address of the first element that you're sending, and then the communication systems can use the data type to identify exactly where everything needs to go. Okay, so let's get concrete. So here we have MPI type struct. This is the MPI function which creates our data type. So let's walk through its arguments. So the first one is count. So this is the number of elements, and the elements can be blocks. So they don't need to contain just one data type. They can contain multiple data types in a contiguous array. So that's count. Then block length, this is an array with the number of elements, storing the number of elements in each block. Indices is an array of byte displacements of each block, and we use an MPI underscore A int data type here because these are memory address locations, so we should not use a conventional integer because it might not be able to hold the data. And to use the information needed to calculate these, we can use MPI underscore address, which is a special function to extract addresses. Then the next argument is alt types. So this indicates the type of each block and the new data type we are defining, whether it's integer or float. And if you like, these data types can be data types created by previous calls to MPI type struct. And then finally, the output of this whole function is new type. And this new type, once we create it, we actually have to sort of activate it using MPI type commit and disactivate it. Now, to make it a little bit clearer, in our particular example, all block length entries would be 1 because we just have a float, and integer, and we do not assume that even though A and B are both floats, we do not assume that they are contiguous in memory. So we cannot treat them as an array of 2 floats. Okay, so to make this all a little bit more concrete, let's look at the actual source code, and things should become much more clear. So here's a function which will build my type. This function takes an input, the pointer to A, pointer to B, and pointer to N, and the output will be the data type that we create. So we create the arrays, which are dimension 3 because we have 3 items. The block lengths, we define them to be 1 because each one of these A, B, and N is holding a single type. And here I create my type list. So the first element is float, second element is float, third element is an integer. And here I'm using conventional MPI data types to define them. Then displacement. So I need to know how are A, B, and N arranged in memory. So the first element A, I assume it's at the start at 0. That will be the first displacement. And then to calculate the second displacement, I use the MPI address call to extract the address of A pointer and address of B pointer, storing these in start address and address. And to calculate displacement, I just take the difference of this and that. And similarly for the pointer to N, to calculate displacement 2, I take the address of N pointer minus the start address. So this gives me the relative displacements of the data. And now I call MPI type struct. So I have 3 elements. Block lengths, these we have defined to be 1. Displacements, we have just computed them here. Type list, types are here. Float, integer. And I call this and I get a new data type. And once I have created this data type, I need to activate it. And I do this with MPI type commit. And then this will be my output. And here I have defined the data type. So how would I use this data type in my actual program? Well, here I have a function called getDataFree, and if you remember the previous lectures, we had other functions, getData, which were communicating A, B, and N between them. And in this case, we were using integration as our example, so A and B were the two limits of integration, and N was the number of trapezoids we used to approximate the integral. So I have getData, I declare an MPI data type object, and here I do some input. So if the process rank is 0, I read in what A, B, and N should be. And then I call the function I just defined. So build derived data type. I provide the pointer to A, pointer to B, pointer to N. And this will return the data type that I need. And once I have this data type, I call an MPI broadcast function where I send this whole set of information, A, B, and N, using the data type I just defined. Message MPI T. And here I provide the pointer to A, so I provide the pointer to the first element in our complex type. And that's all I need to do, because then the relative arrangement of B and N in memory is going to be contained in the data type. And the important thing here is that in previous examples, we would have needed 3 MPI broadcast calls to transmit A and then B and then N. But in this case, I can do it all in one call. Now, to make this concrete, if you are doing this kind of communication only once in your program, it's probably too much of a bother to go through creating, a special data type and then using it. You might as well just call MPI bcast 3 times, and it's going to be very quick. On the other hand, if you have an MPI program which calls a certain MPI routine, a large number of times, where it's a significant chunk of your runtime, well, in this case, reducing the number of broadcasts you're using might be very worthwhile. So in this example, it's probably not that clear, but in something more realistic, that would make a big difference. Okay, so I have just shown you a way to build the most general user-constructed data type you want. So pretty much anything that you like, you can build that way. But that's actually a bit of an overkill. It's too general, and in most cases we need something simpler. So MPI provides us with a number of very useful, simpler data type constructors, and these are MPI type contiguous. So this is sort of the trivial one. It's just built a derived data type whose elements are contiguous entries in an array. But the reason that's not very useful is that you can just use MPI Send and MPI Receive in that case, as I've shown you before. We're using the count parameters to say how many items you're sending. So it's sort of silly to actually build an MPI type contiguous data type, but it is there for completeness. Now, another much more useful one is MPI Type Vector, because this can be used to handle equally spaced entries in an array. And this is really great for handling columns of matrices and things like this. And finally, there's MPI Type Indexed, which can allow you to create a data type for arbitrary entries of an array. So this is the most general case, but this one still assumes that all the types of your array are identical. So let me illustrate the usefulness of this. So this is how these data types become useful for matrix operations. So to remind you, the C language stores 2-dimensional arrays in row major order. So all computer memory is 1-dimensional. So anytime you have a 2-dimensional matrix, it has to actually be stored in 1 dimension. And then the order of the storage matters. So in C, you can see that element 2,3 is preceded by 2,2 and followed by 2,4, so that the last index is the fastest varying one. So if let's imagine that I have defined some matrix, 10 by 10 matrix, and I want to send the third row of A from process 0 to process 1. Well, this, because we are sending rows and rows are contiguous, then we can do this using standard MPI Send and MPI Receive. So in this case, I provide an MPI Send. I provide the address of the first element of the row, and then I just say, from this address, send 10 floats. And then on the receiving end, I also say, start from address of the third row and send 10 elements. So I could have used type contiguous here, but again, it's just not necessary. I can use send and receive. So as long as I'm sending rows, this is perfectly fine. But what if I want to send the third column of A from one process to another? Well, then those entries no longer form a contiguous block in memory. So I cannot use a single MPI Send and MPI Receive. So this is where MPI Type Vector comes to the rescue. So let's discuss this data type in more detail. So you create this using MPI Type Vector, and the arguments are count. This is the number of elements, number of blocks you're sending. Block length, this is the number of elements in each block. And then you have stride. So this is the number of elements between the start of each block. So this is what allows you to handle the column. And then you have the old data type. So this is the data type of the matrix in our example, whatever the matrix is made out of, and then the new data type is the resulting MPI type vector data type you obtain. So using this is how you would send a column then. So in my code, after I define my matrix, I define MPI type vector. So this vector has 10 floating point elements, and each element, each block contains just one floating point. And then the stride between the elements is 10. So this is how I get a column of a matrix. And here I extract, so this is the output, this is the column data type. I have to commit this data type to actually register it with MPI. And then here's my operation. I do a single MPI send, but now instead of sending MPI float, I am sending a column MPI data type. The address is the beginning of the third column, so 0, 2, and I am sending one of them. And on the receiving end, I have the same address, and I receive one column. So in this case, I am able to do a single MPI send and a single MPI receive to send non-contiguous data. And finally, just for completeness, I don't use this very much, but in the work I've done so far. But let's say that you have some complex subsection of your matrix which you need to send. Well, you can use type index, where you provide the number of blocks and then the length of each block. And finally, you have an indices argument where you specifically provide in an array the relative displacements between your blocks. So in this way, you can describe any pattern you like. And one important point, whenever you have MPI send and MPI receive, you don't have to have the same type on the same end. So let's say you want to do a transpose. So you want to send a column from process 0, and then at the receiving end you want to store this row. You can certainly do this. So here I am sending the first column, and this is received as 10 floats starting at the address at the beginning of the matrix. So this will take the column of the matrix in process 0 and store it as a row of the matrix in process 1. So sometimes this is a neat and quick way to actually do a transpose using an MPI communication. Now the important thing is that the types must be compatible. So here this type holds 10 floats, and here this type holds 10 floats, so that there's enough memory so that when I take the data I'm sending, I have enough space to store it. If this did not have 10 floats but something else, if this was smaller, then I would have overflow, and I would be writing outside of arrays, and that's clearly a bad thing. So you have to be a little bit careful when doing this. But this is only possible for MPI send and receive. If you try the collective communication using, it would just not be possible. And MPI bcast, if you call it, it has to have the same data type across all the processes. Now, there is an alternative to this, which we just don't have time to get into. But it is possible to take some non-contiguous data and pack it into a single contiguous array using an MPI called MPI Pack. And then once you pack it into a single contiguous buffer, you can send it and you can unpack it on the other end. This is just an alternative approach. And it has certain advantages and disadvantages, but mainly there's some overhead to actually packing the data. So if you're sending something once, it might make sense to do this packing. On the other hand, if you're sending a certain data pattern multiple times, you want to use a user-defined data type instead. So this is something to keep in mind. I won't have time to cover this in more detail. Okay, so here we have finished with part 1 of this lecture with user-defined types. And now we move on to user-defined communicators. So let's explain some of the concepts here. So what are communicators? Well, processes in your MPI run can be collected into groups. So a group is an ordered set of processes. Each process has a unique rank in the group. If there's P processes in a group, then the ranks will range from 0 to P minus 1. And then a communicator consists of a group and a special context object which actually holds the information for MPI about the communicator. So a process is identified by its rank in the group associated with a communicator, and MPI Comm World is the default communicator, whose group contains all the initial processes. And this is so far the only communicator which we have seen in our examples. So this is why MPI Comm World crops up a lot in our MPI Send and Receive. It just contains all the processes. But what if we want to have a different communicator which holds fewer processes or holds different processes? So why would we want to do this? Why should we complicate our lives? Well, there's a number of possible reasons. One is you want to achieve modularity. So let's say if you're using a library, it might make sense to have the library exchange all its communications in its own communicator, whereas the application works within another context. Sometimes you worry about messages clashing with each other. Whenever you do an MPI send, you want to ensure it gets paired up with a right MPI receive. Now MPI provides tags, which you can handle, but sometimes they are just not sufficient or they are too complicated to use. So if you put one set of communications if you have one set of communications use one communicator and another set use another one, then they will never clash, that they will never end up conflicting with each other. Another reason to use a communicator is when you want to restrict a collective communication to a subset of processes. So we have seen in lecture 2 that collective communications are very, very useful, but sometimes you just don't need to involve all your processes in them. Well, if you only want a subset, then you have to make a separate communicator. And the final point is you might want to create a virtual topology that fits the communication pattern better. And I'll get into topologies in a second. Okay, so how do we then deal with groups and communicator operations? So here's the first MPI functions I will introduce you to. This is a function which, given a communicator, extracts the group associated with it. So you provide a communicator, and this gives you the group of processes which is associated with that communicator. What about if you want to create a new group? So let's say you have you want to create a new communicator. So to do this, first you have to extract the group of the old one using MPI Comm Group, and then you use the original group. You provide this as an argument to MPI Group Include, and this allows you to make a new group. And how do you create it? You provide, well, first of all, you specify how many processes you want in a new group, and then you specify a ranks argument which will list the processes to be included using their index in the original group. So once you do all this, you will create a new group where process I has rank I in the original group using this. Actually, I think it should be ranks here instead of rank. Okay, so once you have created this new group, you can create a new communicator using MPI Comm Create. So you always have to provide the old communicator you're creating the new communicator from. You provide the new group, and you get a new communicator. So this will associate the context of a new group and create new comm. And all the processes in the new group will belong to the underlying communicator. So this is a collective operation. So let's say if you are starting from the original communicator, MPI Comm World, you have to call MPI Comm Create on all your processes, all the processes involved in MPI Comm World. That is a requirement. Okay, so to make this more concrete, I think this will be much more clear once you see an actual example. So in this example, I have 8 processes, and I want to create 2 separate communicators. The first communicator, which will contain processes 0, 1, 2, 3, and then the second communicator will contain processes 4, 5, 6, 7. So how do I do this? I create some MPI group objects to call the original group and the new group. This will be, I declare a new communicator, MPI Comm object. So I initialize my program, I figure out how many processes I have, so I figured out the rank of the process, which is calling this code, and then I obtain the number of tasks in total I have. Now here, this code assumes that there's exactly 8 processes, so I have a simple check here just to make sure it's true. So if I don't remember to start this program with exactly 8 processes, I get an error message and I exit. Okay, so here I create my group. So I take the original communicator. Okay, so first I have the original communicator, and I extract the group associated with that communicator using MPI Comm group. Next, once I have the group, the original group, I want to create a new group. Now, the new group will be different depending on which process I am on. So if I am on 0, 1, 2, 3, I want this if statement to be triggered. On the other hand, if I am process 4, 5, 6, or 7, I want the else to be triggered. So this is what happens. So then on processes 0, 1, 2, 3, this line gets executed. And this line creates a new group using the ranks from the old group. This group contains four processes and uses the ranks 1 array, and ranks 1 contains 0, 1, 2, 3. So this is what happens on processes 0, 1, 2, 3. They get a new group containing processes 0, 1, 2, 3. And then if rank is 4, 5, 6, or 7, I create a new group, and then the ranks array has 4, 5, 6, 7 in it. So once I have done this, I call MPI Comm Create. So notice that I am out of the if statements now. So all the processes in MPI Comm world call MPI Comm Create, and they create a new communicator. But this new communicator will bind together processes 0, 1, 2, 3 if this line is called on processes 0, 1, 2, 3, and then it will bind together processes 4, 5, 6, 7 if this line is called on 4, 5, 6, 7. So once I have created this new communicator, I can now call MPI all reduce. And what this will do, even though it's a single line, on half the processes, this will do a reduce on processes 0, 1, 2, 3. And on the other half, on processes 4, 5, 6, 7, this will do a reduce on processes 4, 5, 6, 7. So in this case, it's doing a sum, and we had the send buff was just a rank, and then the receive buff was an integer. So it sums up all the ranks. So if we were to print this, then on processes 0, 1, 2, 3, the result would be 6, because it would be 0 plus 1 plus 2 plus 3. And then on the other processes will be sum of these numbers. So here we have, using new communicators, we have managed to split our reduce operation into 2 separate reduce operations. The first reduce operation operates on the first half of the processes, and the second reduce operation operates on the second half. Okay, so so this is the most general way to create new communicators. But again, just as we saw with data types, the general way might be a little bit too tedious. So there's a convenience function, if you like, called MPI Comm Split, which allows you to create new communicators by splitting the existing processes by colors. So color is just an index which allows you to split the groups. So what this MPI Comm Split call will do, it will partition the group associated with Comm, which is the original communicator, into disjoint subgroups, one for each value of color. So and color is just whatever you want to use to identify a particular group. And then there's some things like what happens if you have a tie and that kind of thing. So those are just some details. But this will become much more clear once I show you the actual use of this. So this becomes very useful if you are dealing with matrices. So for example, what if you want to create a separate communicator for each row of a matrix, right? Well, in this case, the color, you can just use the row index as the color, right? So this will allow you to call this function just once and get a separate communicator for processes in this row, processes in this row, and processes in this row. So let's imagine we have, let's say, 9 processes, and we want to organize them into groups of 3 where processes 0, 1, 2 are in this one subset, processes 3, 4, 5 are in the second subset, and 6, 7, 8 are in the third subset. We want 3 different communicators. So MPI Comm Split will just allow us to do this in one go instead of bothering with MPI Group Include and MPI Comm Create. So let me show you some code which illustrates how this is done. So I start off, I declare MPI Comm, which will be my new row communicator. I do the usual initialization. And now all I need to do to create the communicators is I identify the row I'm in. So I compute my row, which is just my rank divided by Q. So if I am process, so remember that in this example, so let's say if we had 9 processes, then Q will be 3. So then for processes 0, 1, 2, my row is 0. So all those processes get color 0, if you will. Then processes 3, 4, 5 get color 1, and the rest get color 2. So now I call MPI Comm Split, and this will take the original communicator, MPI Comm World. It will use my row as a color. My rank is also provided here, and the result is my row comm. So my rank is necessary to split any ties that occur. And then I can, to test the new communicators, I can call MPI Comm Rank to find out what is the rank of the process within this new communicator I created. And then we can do a test. We can have the first communicator in the first process in each new communicator do a broadcast. So I have an if statement. If the rank in the new communicator is 0, I initialize some data to be sent, and else I set this data to be 0 because I'll be receiving. And then here MPI broadcast is called, where test is broadcasted out from process 0 in the new communicator to all the other processes. And then there's some printout. So for the example of a 3 by 3 matrix of processes, when I call MPI bcast, this means that actually 3 separate broadcasts are happening, 1 broadcast for each row of processes. Okay. So this is how you make new communicators, but even this is a little bit tedious. So could one make it even simpler? In particular, what if you are working with some very standard things like Cartesian grid topologies? So let's consider a case where your processes are arranged on some kind of a regular grid, 2 by 2, 3 by 3, 3 by 4 by 3, whatever the number of dimensions you want. Well, for this special case, there is the Cartesian topology mechanism provided by MPI, which is really meant to save the programmer a lot of work. So, because you will shortly see how much easier it is to define groups and subgroups using this approach. But there's a deeper reason why the Cartesian topology might be very useful to you, and this is that your MPI implementation may assign processors to fit the topology optimally. So let's say if you have if your processes are on a 10 by 10 by 10 grid, let's say you have 1,000 processors, well, there is probably a way to distribute those processes among your HPC cluster in an optimal way. So if you use the Cartesian topology, you can at least hope that MPI has some kind of an implementation to distribute your processes in the most optimal way to the actual hardware. Now, whether this is actually implemented will depend a lot on the MPI you are using, and there's no guarantee that this will be implemented, but at least you're giving MPI a chance to do it. Okay, so the Cartesian topology allows you to address your processes in a more natural way. So let's say I have 12 processes on a 3 by 4 grid. Well, in default MPI, They are just numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's fine. But as a programmer, it might be more convenient to have a two-dimensional index for them. So think of this as process 0, 0, this as process 0, 1, so row 0, column 1, this is process 0, 2, and so on. So the Cartesian topology allows you to do this. And this is how you create a Cartesian new communicator with Cartesian topology of arbitrary dimension. This is a very simple function. You provide the old communicator. You specify how many dimensions there will be in a new communicator. And you specify the array which contains the dimensions. You can also specify whether your array is periodic or not, which we'll see in a second what that means. There's a reorder flag, so this indicates whether the original processes can be reordered or not. And a reordering might be good, again, tying this to this idea that if MPI can find a better fit between the processors and the hardware, then you want to make reordering possible. And then finally here you get a new communicator, which has the communicator data type, but it's a special communicator. It's a Cartesian communicator, so it has some additional features which you'll be able to take advantage of. So once you have created this communicator, you can now translate between the two-dimensional and the one-dimensional pictures. So you can, for example, say, given your rank, so given your integer rank within the newly created communicator, you can obtain the two-dimensional or multi-dimensional coordinates of the process. So this is the way to go from this to this, from 0 to 0, 0. And then you can go the other way as well. So this is a translator from MPI card rank, means you can provide your two-dimensional coordinates and you can obtain the one-dimensional or multi-dimensional coordinate here, and you can get the one-dimensional coordinate and output. So this is the coordinates to rank translator. So this is a way to change from a multi-dimensional picture to a one-dimensional. And here's a way to create new communicators. Now, this is something quite convenient. So let's say you have a multi-dimensional Cartesian topology and you want to create a communicator using some slice of this old communicator. So let's say you have a two-dimensional, row by column set of processes, and you want to create a communicator for each row. Well, we have already done this using MPI Comm Split, but now we will see how much easier it is in the Cartesian topology. So this requires just 3 arguments in this case. You provide the old communicator, and then the output will be the new communicator. And the integer free coordinates, this is just an array which specifies which dimensions are free and which are not free. So in a two-dimensional case, this specifies whether you want the new communicator along the columns or along the rows. So this is a pictorial representation which might make things a little bit clearer. So if I have, so let's say this is the communicator which I have. This is a 3x3 example, and I have these processes in the communicator identified with a two-dimensional index 0, 0, 0, 1, 0, 2. And let's say I want a new communicator which holds the processes in each row. So here I use different colors to indicate that we'll have the green communicator holding processes 0, 0, 0, 1, 0, 2, and then another new communicator holding 1.10, 1112, and finally one for 202.122. How do I do this using MPI Card Sub? All I indicate is I define a 3 chords two-dimensional 2-item array, and I say that along the rows I don't want any freedoms. I set this to 0. But along the columns, I do want freedoms. I set this to 1. So the processes the new communicators can range freely along the columns. So column 0, column 1, column 2. But then the rows are held fixed. So row is held fixed, row is held fixed, row is held fixed. So this is how you understand these 2 items. So by defining these 2 elements of this array, I call MPI Card Sub, and this gives me a row communicator which holds the processes in each row. Okay, so nearing the conclusion of this seminar, let me now show you maybe more complicated code which illustrates this. So in this code implements an algorithm which builds a two-dimensional Cartesian communicator from MPI Comm World, it prints the topology information for each process. Then it uses MPI Card Sub to build a communicator for each row of the Cartesian communicator. It carries out a broadcast using these row communicator, prints the results, and then it uses MPI Card Sub again to build a communicator for each column. It carries out the broadcast across each column communicator, and it prints the results. Note that we assume here the number of processes P is a perfect square. Okay, so we start with our code. So this is all pretty standard, except we define the new communicators for the row communicator and the column communicator. So first we do the MPI Card Create. So we use the MPI Comm World. This is the original communicator. And I want a new communicator, which is so we take the square root of the number of processes. Again, we assume it's a perfect square. And then the new communicator is two-dimensional Q by Q. So I have a two-item array dim sizes. So I set them both to Q, provide the argument here. Now for wraparound simply means whether your array of processes is periodic or not. And we will see in a second why this matters. So here I define this to be 1, so it is periodic. Reorder, whether I define it, whether I want it to be reordered or not. And I get my grid communicator. So this is my original Cartesian communicator, which still holds all the processes, except now they are arranged in a two-dimensional grid. Once I have this new communicator, I extract my grid rank, so each process identifies its new rank within this communicator, and this rank might be different from the original rank in the MPI Comm World if I allow the reordering to occur. So it's important to check what is the new rank. And then I call MPI Card Coordinates to identify what are my coordinates within this new two-dimensional communicator. And I can also here is an example of translating from the coordinates to the grid rank, and this should be the same as the grid rank obtained in MPI Comm rank. And finally, there's a printout to just print out all the data which we have determined to make sure that everything checks out. Okay, so once we have the full communicator, let's now create sub-communicators. So first we create a communicator for the columns. So we define the freedom variables, degrees of freedom, if you will. So along the rows, we set this to be 0. Along the columns, we set this to be 1. We call MPI Card Sub, and this will create a new row communicator. And then I do a test broadcast. So first of all, if my coordinates are 0, then I specify this as an item which has to be sent. Otherwise, I make it -1. So then, for the broadcast to work, the row test has to change from -1 to whatever I'm broadcasting. So I call MPI broadcast, and then I print things out to make sure that everything checks out. And then, to do it in the other way, I now create my column communicator. So I define I switch around the degrees of freedom. I create the new communicator. I create the data to be sent, and I call MPI bcast. And finally, I print out the result to make sure that everything checks out. So I hope you can see from this that MPI Card Sub provides just a really easy, straightforward way to define new communicators along the rows and columns, or just slices in general of your multi-dimensional Cartesian grid. So we are fairly close to the end. Let me just cover a few salient points about Cartesian topology. One important point to note that there is no MPI Card Send or MPI Card Receive, which would allow you to send a message to a process using the multi-dimensional index in your Cartesian topology. So you still have to use standard communication functions. So, but there is a convenient way to obtain the rank of the desired destination and source process from your Cartesian coordinate grid. And usually, whenever you're dealing with a process in the Cartesian grid, you usually want to communicate between the neighbors. So you want to have your neighbor to the left, to the right, and up and down. So the way to get the to figure out who your neighbor is, you can use a function, MPI function called MPI Card Shift. So here you, what are the arguments? So you have your Cartesian communicator. You indicate the direction you want to shift, so whether you want your neighbors along the row or along the columns. And in general, this can range from 0 to n-1 for an n-dimensional Cartesian grid. Then you can specify displacement, whether you're shifting upwards or downwards, and how many elements you want to shift by. So usually this is 1 or -1. And this is where the periodic wraparound matters. So a periodic wraparound means that if you are at the edge of the process grid, if periodic wraparound is on, you'll get around to the other side, and this will be your neighbor. On the other hand, if this is off, then you'll get a null neighbor. One that doesn't exist. There's a special procedure for this. So the outputs you get source and destination. So you actually get two numbers, not just one. And this is because the output is really slated to work with MPI Send receive, which we have seen in previous lectures. So source is the rank of the process to receive data from. And this is obtained by subtracting displacement from the coordinate determined by direction, and destination is the rank of the process to send data to. So basically sort of assume that the source is the process behind you, and destination the process in front of you, if you like. This is just a very common combination which shows up. So this is why there's two outputs instead of one. If you are at the edge of your process grid, then the source and destination might be undefined. So you get MPI proc though, if you're outside the grid. Okay, so now to illustrate this with pictures to make it clear, let's say I have a 3x3 grid of processes. So let's say that I have process 0, 1, 2, 3, 4, 5, 6, 7, 8. And these are identified by 0, 0, 0, 1, 0, 2. Now if I call MPI card shift on each of these processes, so here I'm shifting by 1, and I'm shifting along dimension 1, so the second dimension, which is the columns. This tells me that my source here, so for process 0, my source will be the item to the left of me, which because of wraparound, the wraparound is, so the periodic conditions have been turned on in this example. My neighbor to the left is actually process 2, and my neighbor to the right is process 1, so destination is 1. For this process, source is neighbor to the left, so it's 0. Destination is neighbor to the right, which is 2. And then for this process, source is neighbor to the left, which is 1, and destination is neighbor to the right, which, because of the periodic boundary conditions, is process 0. And similar pattern holds for the other rows. What if we switch things around and notice that, rather we don't switch things around. Let's say it's a different communicator now in which I don't have periodic boundary conditions. So I get the same results as before, except that when I want to have the destination, this lies outside of the process grid, I actually get -1. This means that it's a non-existent process. And so this is just a way to indicate that there is no actual neighbor. And now I switch things around, so I change the directions. I change the directions to 0, so now I'm looking along columns. And also I also change the displacement, so I'm going the other way. So let's see how this works. Let's now focus on process 4, process 1, 1. So I'm now looking at my neighbor, but because it's -1, I'm going downwards now. So my source is 7, and my destination is 1. For this process, source is 8, destination is 2, and so on. So, if you want a bit of a deeper understanding of this, you can just try different arguments and sort of work with pencil and paper, or just to get a hang of what these directions and displacement mean. So this is the end of the lecture. I hope that I have introduced you to the concepts of user-defined data types and user-defined communicators. So thank you very much.